Awesome. Not that it matters, but my body thinks it's 3 a.m., just so you know. But why don't we get going? I noticed that the last session I went long, so I want to make sure we be able to get some time in. This focus is going to be on Java memory and garbage collection in general. When we are concerned about that, the most common time we're concerned about that is production. So that's where our focus is. I will have some advice towards the end of things you might consider or look at as a developer, but for the most part, we're looking at what is this JRE thing and how does it work and how does memory get managed. And I'll update us then as well on Java 8. I could talk a little bit 9 stuff. I don't know if I have slides on that. We'll see. All right. So the first is focused on the production environment. The other thing I want to add is I've been talking about the JRE for some time, memory management for some time, but some of this I've changed my terminology to match this book. So you'll see some very confusing literature out there. Probably the most confusing of words you can use when dealing with this subject is that of tenuring. I don't know if I even like that word, but I'm going to use it very specifically and according to this book, and my goal is to bring focus for words to have meaning in here, all right? So that's where you'll see more detail if you want to dig in deeper on this subject. We have a lot of things to go through, and I'm not going to read that. Just real quickly, if you're dealing with memory issues in a production environment, there's more things to the JRE. What are you running on for a VM? What is the platform it's on? How is it provisioned? There are other things to consider. Oftentimes, the JRE is blamed and it's not the thing. Now, that's as much words as I'm going to give to that. I'm going to focus on the JRE. But if you're truly debugging an issue, you may want to be looking at whether something's over-provisioned. You may want to be looking at I/O. You may want to be looking at whether whether you have something that's CPU bound. There are other details to be concerned with. Just bring that to light real quickly. Also, when we're dealing with memory in particular and how we get performance out of the JRE, there are 3 axes like we would normally expect, right? Now, some of you would expect, hey, I'm in a data center and I have unlimited amount of memory, so we can take that off the list. I have to pick one of the other 2, right? I used to, years ago, work for GoGo, which provides in-flight Wi-Fi entertainment in airplanes. Now, what's great about working on that system is there's only like 400 people on the plane. Right? So the scale is limited. It's restricted to the number of devices in the plane, and oftentimes it's very low. It's in the hundreds. But as a negative, I was restricted to 512 megabytes for everything that I wanted to do. And so that became the concern that I had for that particular application. So as you can see, it varies. You know, if you're running on an Android, if you're running in a data center, you have other things to deal with that you may want to be concerned with. And that'll play a factor into how we deal with some of the concerns that we'll bring up. Lastly, this is automatic for you now. It used to be experimental. Now it's automatically there, but it's worth noting. Some time ago, we went from 32-bit to 64-bit, and magically something happened. I had the same application. I literally updated the same version of the VM from a 32-bit version to a 64-bit version, and what happened? Its memory consumption at the system level was twice as much, magically. And it should make sense. We went from 32 bits to 64. But we have an interesting thought there, right? And that is, if you're using less than, as you can see up here, 4 gigabytes of memory, you never tap into the higher order bits. And so this flag, which is automatic for you now, is called compressed oops. And what that means is use the lower order bits and the higher order bits for 2 different memory address spaces, even though it's just 1. So 1 memory address space can hold 2 addresses, if you will, as long as we're underneath 4 gigs. So that's a magical component. It's worth kind of at least bringing awareness to. It's not something you tend to deal with anymore. So let's talk about memory management. The first is, isn't it awesome? We're using Java. We don't have to worry about it, right? We don't have any mallocs or frees. We don't have to free anything. It's just magic. It's awesome. Isn't that true? Well, you're smiling, so apparently there's more to it than that. There is something really neat and magical about the JRE and what it can do for us, and we're going to focus on that just a little bit. We have this thing. Now, there's some hard conversation we need to have, and what I want to talk initially is about theory. I will bring it into reality, but if you don't mind, just for a couple slides, I want to talk about some theoretical ideas and concepts. So if we can imagine that we're going to keep track of memory, like how we allocate and then deallocate memory, and something has to manage that, you can imagine a garbage collector that may mark and sweep. In the early days, we actually kind of did this. This is not how it's done today, but just bear with me for a moment. We're going to go through and we're going to mark things. Now, what's your concern when you're dealing with memory management? Your big concern should be that it's a necessary evil, but you'd rather not, right? It's time spent doing stuff that's not business, but yet necessary. So there's this interesting balance that we're trying to play with. Now, what can we do theoretically in order to reduce our overhead? Well, we might be able to divide or fraction things out such that I can visit things less often. And if I visit something less often, then I'm dealing with it less often. I can reduce overhead by fragmenting, if you will. So, if I mark and sweep, I could go, are you still referenceable? Yep. Are you still referenceable? Yep. Are you? I'm going to mark you. You're marked for death, right? It's like, bring out your dead. Right? You got to sweep through and clear it all out. We get into some interesting conversations, which is debatable. I want to mention real quickly that sometimes these topics, for whatever reason, get me into some interesting arguments with folks who know something for some reason. I will focus most of my talk when we get into the real stuff on the Sun, now Oracle JRE, and the Open JDK. There are some differences out there that are worth knowing about. Azul has some pretty interesting things that they do. I also want to advertise that I'm not a systems engineer or a JRE engineer. I have many friends that are, but that's not my field. What I am going to share with you is things that I had to get into in order to help clients or help myself out in a production environment. And I've learned a lot from dealing with like Kirk Pepperdine and with Andre and a couple of others that work in that field. So we have this mark and sweep concept, right, that we're going to be able to divide things out. There's some additional theory that I don't actually remember where I get the details from, but we can talk through it, right? It tends to be that when we create an object, we can assume that it's going to live for a very short period of time. We can also make another assumption, and that is if an object lives for a long time, it tends to live for an extremely long time. This notion allows us to fragment in a different category. And we're going to bring that up in a second, but let's talk it through for a second. If I'm building a Spring MVC application, and I have a controller, when I create an instance of the controller, first of all, how many of that particular type of controller are there in the JRE? It's a singleton. It's probably one, right? How long does it live? For probably the life of the JRE. I will spin up a JRE that has Tomcat in it. It's going to spin up an instance of this application, which is a Spring MVC controller. I have this controller object. I get one, and it's going to last forever. Now, we could obviously find edge cases where that's not true, but that's the most common case. How about the HTTP servlet request object? How long does it live? You've got a request that comes in, a response, and it's gone, right? It's like, how many are there? It depends on scale. Depends on a number of things out of our control, but one can imagine at a really high scale, request-centric architecture, like a microservices architecture, if I want to be one of the cool kids today, it could be millions over a set of time, right? Millions compared to one. millions of short-lived objects compared to one really, really long-living object. Now, this has been the theory for some time about how programmers program. In addition to it also probably makes sense, just talking it through. Now, there's a really interesting thing that's happened with Java, and I may not look this age, but I've been working on the GRE in the Java world since '97. Whoa. There used to be a time when you had to do stuff to make things faster, right? And those techniques would be ridiculous today. And the problem that we have is we have some of the old folks teaching the younger folks bad habits. Because that would not be what you want to do. So we'll talk it through a little bit, but that's the concept, right? We have a mark sweep model. We're going to make that real in a second. We have longer living objects. We have shorter living objects. So we can divide the space. Now, from a theoretical standpoint, all programming languages or VMs have the same kind of model or technique. I could change this talk into a .NET talk, and the one difference would be there would be 4 compartments instead of 2. The idea, though, is that I have generational compartments. When we talk about Java, we tend to talk about 2. Frankly, oftentimes there's more because we don't include perm space in that, but you could think of it as the same. It's a heap-like thing. Oh, I forgot. Let me have one quick conversation kind of off slide to make sure we're on the same page, all right? Heap and stack. What is a heap? I just want to make sure we're all on the same page. I'm going to make sure everybody leaves with something, right? A heap, what is that thing? It's kind of this non-structured amount of memory that we can create objects out of, right? It's intended to be non-structured. We can get into debates, and people often do. It's got to be this contiguous set of memory. That's a VM-specific thing. That's not in the spec. It doesn't have to be. In fact, you'll see that we tend to deviate from that in the modern GCs, okay? But it used to be, and there's some value to a contiguous space we're going to talk about in a second. So we have this non-structured space, this heap of memory, this grab bag I can just start dicing up. And it tends to be that we allocate off that. You'll see in a second that it's actually faster to allocate memory in Java than it is in C. How crazy is that? Doesn't mean that Java's faster though, right? Are we okay? Just means that it's really simple. If I've already got a pre-existing memory space that's already allocated to a process space, that I can increment a pointer really damn fast, right? That's all it means. Doesn't mean other things than that. What is this stack thing we speak of? What is this? We got 2 different types of memory we tend to care about. What is this stack? It's more structured, right? We have a stack per thread. When I make a call into a function, technically what happens is a stack frame is created. A stack frame is pushed on the stack. Inside of the stack frame would include things like variables that were passed or references, whatever. There's a memory that manages whether you have a reference or an object passed by value that's in the stack frame. All the private member variables that are defined, those are in the stack frame. Something has to hold that. That's a stack frame. I assume there's some people in here that may have seen a stack trace or two, right? What is that? It is an exception occurred, and we are popping off the stack until we get an error handler. Hopefully it's not the main process, right? And that's what's happening. You're popping frames. So we have this structured process. We have a stack. We have stack frames that get pushed into the stack. Let's put it all together. How does it work? I have thing T equals new thing. When you see the word new, you're thinking allocation out of the heap. Thing T equal new thing. I have thing T, I have a reference of T, which is going to be on the stack, inside the stack frame. It's going to be referencing a memory location that was created by the new thing. Everybody good? Okay, this is super easy stuff, right? So now we have 2 compartments you see up here. I have my new space and my old space. We could go old school. Years ago, if you see documents that are still out there, the young generation and the old generation. It's the same thing, right? We just changed the names so that we could confuse more people. Well, we got to keep, we don't want too many programmers. We got to keep the money good. Joking, relax. Now, that is all the compartments. When we say MX, this is everything. When we say MX, this is everything. Now, we are going to break up the new space a little bit further than this. But there's this other space, which is the perm space, which is heap-like, which we'll talk about in a second. With the new space, we can divide up the space into 3 more spaces. It's still considered new. And when we look at the flags that I'll introduce in a second, you'll see that I'll have new ratio and new size. That is the new space. It includes those 3 compartments, the Eden space and 2 survivor spaces. Now, Eden. Clearly, any object is created in Eden, right? That would make sense. I commonly get asked the question, is it possible to have an object so big or Eden space so small that an object that needs to be created can't be created in Eden? I believe the answer is yes, but it's evil. All right, not too many religious people in here. Good. All right, so we have the Eden space. New objects are created in Eden. I mentioned it before. It's super simple. I have a pointer at Eden. When I say thing t equals new thing, the size of thing, pointer moves. I create a new thing, pointer moves. The size of thing. Super easy. That's how great it is to have a linear space. I can just increment the pointer by the size of the object. Way fast. All right, there's some huge value there. Now, I've mentioned time already a couple of times. That an object that lives for a long time tends to live for a very long time. But time is really not a factor, and let me demystify one more quick thing. When does a garbage collection occur? Is it a matter of time? It's not. It's a matter of running out of space. So I said thing t equals new thing. I had a pointer at Eden. It tried to move the size of the thing, and it's like, oh, there's not enough space. All right, we better make a space for it. We better do a GC. And we'll go into more details on that in a second, but that's the core of it. GCs happen because I try to allocate into a space that no longer has space for me. Now, it's going to get slightly confusing in that there's a difference between the max of what that space can be and what the threshold currently is at. That is the only confusing part, I think, but it's worth talking about. When we talk about MX, that's the whole space. We could add on top of that perm space. I will move into meta space in a second, but there's still way too many people on Java 7. And the perm space is heap-like, and it's controlled by the process. What's the negative of it? Well, there's a couple things that are worth talking about, and that is, as you might imagine by the name, perm, it is intended for things that were permanent. It was conceived by the designers that this would be permanent things, like class information. Now, there were a couple of points in the history of the GRE where there was a lot of pressure put on perm. The very first time talking to Brian Getz was when we came out with JSPs. Remember that? All of a sudden, we needed to compile JSPs into servlets and then servlets into classes, and then it was a lot of pressure on perm. So things had to change a bit. There is another point in perm where things got challenging. All of a sudden, Spring got really exciting. Everybody loves Spring. What do we know about Spring, at least in the early days? A lot of XML. XML used to be really slow. It's debatable now. I think it's still slow, but that's an opinion. How did we improve XML processing? It turns out that there's probably no verbose way of sending information than XML. And it turns out that when you see a tag, you'll probably see it again. Probably multiple times. So what if, now let's take a step back. Java.lang.string. There's an intern method on string. What is it? What does it do? Java.lang.string.intern. The intern method. What does it do? Lots of input. That is awesome. Yeah. It takes, like the documentation says that it makes sure that there's a single instance of that string in the JRE, but what it does is it takes it and puts it in the string pool. And that string pool, in the early days, was in perm space. String 1 equals string 2 versus string 1 dot equals string 2. What's the difference? Memory reference comparison versus a value comparison. Which one's faster? Yeah, you guys are good. I don't always get that response, but I love you guys were immediate and it was dead on. It's not only faster, the beauty of a memory reference comparison is that it's exactly and always the same amount of clock cycles. It's the same time, always, which is largely different than needing to go char by char until you can verify that all of them are equal, which means it's an undetermined amount of clock cycles or an undetermined amount of time relative to the size of the string, which can get verbose with XML and other things, right? So what happened? We take XML, we say .intern on a string, move it into the string pool. We then can do equal comparisons, and Java XML processing becomes very fast. But our perm space grows into really interesting space. Now the string pool has moved into the old heap space at this point when we get to meta. Might as well introduce that in now. But that's kind of what happened with perm. And the problem is that when I created an instance of perm space, there was nowhere for me to grow. I've allocated this memory for the process. It's not native space. I can't just dynamically grow, and I was kind of host. Like it's whatever the size was created, and then I'm stuck. The only fix is to bounce it again with a change, which is not exactly ideal. Hence the need to move forward into metaspace. These are actually variables that come out of the code. There's a thing called Eden, of course. But then there's flags. I have the new size. The Eden size is going to be equal to the new size minus the 2 survivor spaces. The thing I didn't mention before is the 2 survivor spaces are always exactly the same size. Now, one of the ways you could size the survivor space is you could size it by ratio, which is actually very common. Now, I don't tend to like to memorize things. I got other better ways to use my mind, right? But there's some good rule of thumbs that I think are worth knowing. The first is, and this is kind of a memorization, but I've done it enough times that I know, survivor ratio by default is 32. Okay, but all I need is a stick in the mud, right? I know 32 is the stick in the mud. Now, what I need to know by rule of thumb is that if you make the survivor larger, the survivor spaces get smaller. And if I make the survivor ratio smaller, the space gets larger. So first of all, 32 is the default. A lot of organizations don't change. By the way, when I look into a production JRE, in most organizations, if they let me into their production environment, what do you think is the common configuration? Mostly the default, with the one exception of MX. And here's the thing, right? I don't know if the developer made the choice or the ops person, but like if you ran out of memory or you have problems, what do? What's the most common thing to do? I just want more. Let's turn the dial. I know this dial. I want to make it bigger. Now, bigger may not be better, right? Are we good with that? In fact, I'll show you an example in a few minutes. But oftentimes in a production environment, with a more up-to-date ops team, heavily Java-centric, they might be messing with the collector as well. They might have changed the collector. Maybe they're using CMS. So they'll set MX, they'll set CMS, oftentimes nothing else. So now I know the survivor ratio is 32. If they've changed it, it becomes easy. They'll switch it to 16 or 8, and if they did that, I know they're making it bigger. Right? That's essentially what I know at that point. Useful to know. There's a couple of ways to manage the new space as well as far as sizing goes. I don't know if I really have an opinion on which one's better. One is the new ratio, and the new ratio is the ratio of the new size relative to the heap space. So as you set MX, new would grow as well by what is maximum. The other way is just to set the new size. There is some debate on this particular subject. Two predominant points of argument. There is one school of thought that says, I'm going to set the max new size and the new size to exactly the same. The other is, I'm going to set the new size equal to slightly less, maybe 10% less of the max new size. I kind of fall in the first camp. If I decide I want 256 megs of memory for new, I just say that's max and I consume it. Now, this may not be for all your JREs. I guess I should have taken a step back and announced that first of all. We've been using Java for a long time. You may not have had a problem for a long time. If you have an average low-scale application, which is very, very common, a lot of the things we're talking about, you don't need to mess with. I just wouldn't mess with it. We're talking about you have a need to look at this in a really detailed way because you have a high-scale application, right? And then we'll start messing with it. So let's talk garbage collector again. We're going to start out with the scavenge, that's the old school name, or the minor GC. When does it happen? Thing T equals new thing. I move the pointer in Eden, and Eden's not big enough. I have to do a minor GC. There's a couple of things that happen at a minor GC. First of all, I want to start by saying, by default, the garbage collector you have with the JRE, if you did not change it, is the old parallel GC. The old parallel GC is the fastest minor GC that's possible, that I know of. It is extremely fast and very predictable. There's a lot of people that move to the CMS. I'm going to talk CMS in a few minutes. I do have my friends who I will get in arguments about. But I have my opinion about CMS. My preference is, by default, to use the old parallel GC, which is the default. All right, we'll talk about that further in just a second. So at a minor GC, what happens? You see the fulls in quotes? It is possible that the max new size could be 256 megs. But the current size is 128. And when I hit 128, it doesn't just instantly grow. It goes, oh crap, I better do a minor GC. And it goes through a minor GC and then does calculations on when it should maximize, like how frequent is this happening and that kind of stuff. That starts to get at a level that I'm less familiar with because I'm not the developer at that level, all right? But it just doesn't instantly grow. The concept of full can be confusing. It is not often max. At the point of the minor GC, I take all of the living. Now, I get this question. Are we actually going to move Yes, we're moving objects. Sorry. Right? Are we moving pointer? No, we're moving memory around. We take the living objects in the Eden space, in other words, the referenceable objects, and we take the referenceable objects from the current survivor space, and we move all of that stuff to the next survivor space, and we switch. So the thing to know about survivor space, which is interesting, is that they're exactly the same size, and only one is ever current. Only one is active at a given point in time. The other one is you could consider it hot standby, ready for the next minor GC. Okay? At that point, we make one more determination. And that is, what is our max tenuring threshold? Now, I mentioned very early on, I introduced the book. There are some words I like to be very specific about that I've actually changed myself. It's been years ago for me, but I still hear some abuse on tenuring and on promotions. Remember, if I have an object that was newly created, my expectation is it's going to die soon. Right? I expect, and this is going to be weird, right? I expect a high morbidity rate in new space. Right? I expect it. If you were coding in another way, well, then we might have a problem. And there are times for which that's not true. When can I imagine a use case for which this is not true? One, I have a desktop Java application for which a human is in control of object creation, and it's not a request-centric application. Two, I have a Hadoop application that brings in a ton of memory I'm going to do some MapReduce processes on. They're going to live forever until some answer is created. Great. Those are examples for which I'm expecting objects to live for a very long time. In those environments, I expect, I might have to do some testing to figure it out, but I expect smaller new sizes because I don't know if it matters so much. I'm definitely going to need some old space, and I'm going to expect high promotion rates. So what are these words, threshold, tenuring threshold or tenuring and promotion? An object that I expect to die quickly in the new space is going to be tenured in the new space. I'm going to keep it there. I'm not going to promote it to the old space. Those are the words. I tenure things. I'm moving objects around. In new space is tenuring. I'm tenuring with the expectation that it will die soon. When I promote objects, I'm promoting it from the new space to the old space. When I do a minor GC, I'm going to do a calculation of the max tenuring threshold. What is that? Well, I've worked with it long enough now to tell you the max tenuring threshold by default is 15, which means that objects will be bouncing back and forth until 15 minor GCs occur. In which case, looks like it's going to live for a while. I'm going to promote it. Right? It's a lot like I'm going to visit you, are you still around? And you're like, you're kind of an elderly object. I'm going to move you to where I put the elderly objects. And, Easter and Christmas, I'm going to come visit you. Very infrequently, right? That's the idea or concept. Also, I make one more comparison. It's like when we talk about the age of an object, and we often do, when we talk about the age of an object, it's not really time-based, like you might imagine we use the word age in the English language. It is more like I live in San Francisco, I survived an earthquake, and now I'm 1, right? I survived another one, I'm now 2. Every time you survive a GC, that is an increment in your age, essentially, all right? You guys are not laughing at any of the mild joke attempts, but I'll forgive you now. Okay, so minor GCs, what is this full GC thing? This major GC. Now imagine when this occurs. I said thing t equals new thing. I tried to move an object, I tried to move the pointer in Eden to the size of the thing, and it doesn't fit. I have to do a minor GC. I'm doing a minor GC, and I take objects that are still referenceable from the Eden space and from the survivor space. Now, one of two things are happening here. I'm taking objects and I'm moving them to the survivor space, and one of two things are possible. One is there's too much to fit there. And now I have to go somewhere. I'm going to promote it. Notice how bad this is. I've just promoted objects that aren't elderly yet. So I'm putting young people in the old folks' home, right? The other thing that might happen is I'm old. I've reached the ripe old age of the max tenuring threshold, which is 15. I am now going to move you to the old space. You're going to be promoted. Whoop, I hit the wrong button. You're going to be promoted to the old space. Now, the other thing, I guess I should say there's more than two things, right? The other thing is everything fits. Everything fits, and that's fine. Now, if I go into a JRE running in production and I see under nominal conditions, this gets really complicated, right? Nominal conditions. If I see a max tenuring threshold that's something really low, I'm going to be concerned. If I see a max tenuring threshold of 1, that means that every time I create an object and move it, then I'm going to promote it on the next one. That's concerning. Now, under heavy load, in other words, non-nominal normal conditions, yeah, sure, that's awesome. That's great. The JRE is dynamic enough to be able to handle those details. That is fantastic. You want to be careful about when you're really looking for trends. You're not looking for a moment in time. It can be confusing. It's like if you're looking at the stock market and you're like, hey, IBM stock's at 90. Do you want some? Well, there's lots of things I kind of want to know at that point, right? What was it yesterday? What was it last year? If you get to the technical, I happen to like stocks, so if you get into the technicals, where's support and resistance at? What's the demand on this thing? How liquid is it? Those are things I want to know. What's the trend? Same thing with the Java space. What is the trend of things? I need to know those details. So there isn't like one knob that's just magic for you. You have to put a lot of things together in order to put some thoughts into it. One point that I want to make clear, a major GC, oh, I didn't finish it. I promoted stuff, right? I did a minor GC, and I'm going to promote stuff for one or two reasons. It's old enough, or it doesn't fit. And I'm taking those objects and I'm moving it into the old space, and then, oh crap, that pointer has reached a max for the objects that need to be promoted, hence I need to do a full GC. Notice that a major GC is always preceded by a minor GC. It is the fact that I've promoted objects into the old space, and I don't have enough space for full, whatever that is at that given point in time, whatever that threshold is. I need the space to be reclaimed, and so I do a full GC. It is the only time that we actually do, by the way, if you've ever had a Java experience that's really slow, then you've experienced the full GC. This is a suspend the world moment, right? And so as ops people, we keep dabbling into how can I avoid that? There's a number of things that we tend to do to try to avoid that at all cost. Unfortunately, the lion's share of what I see is guessing. They're like, let's try the CMS collector. Let's see what that does, right? Now, I want to be fair. What I love about what we do, and I'm serious about it, what I love about what we do in our industry, it's this beautiful thing of a combination of art and science, right? Now, but you just can't be all right brain, right? You got to put in some left brain activities. So the left brain activities is I'm going to measure stuff. I'm going to put it under load. I'm going to be looking at trends. I'm going to be looking at numbers and understanding those numbers. I'm going to be doing some analytics. I'm going to look in the production environment on my analytics and go, oh, 80% of my traffic is here and 20% is there. And then I'm going to be hitting the same numbers on my load test in a non-production environment and looking at numbers again. That's the science. There is always a little bit of dabbling in guessing, if you will. Like, hey, can I get some value out of this? But now I have a theory, and it's more scientific, right? I have a theory of, well, I know I'm trying to squeeze this, and I happen to know now that, I'll give you an example, a real-world example. I was working with a pharmaceutical company, and they were having some memory issues. They had this is so old, it was Corba in those days, right? They had some Corba applications, a distributed application. And they did something called an order release. And at the point of an order release for pharmaceuticals, you need to do stuff. There's like a rules-based engine, which means I got a lot of memory that's being consumed for these rules. Do I have a valid prescription? Does the prescription have anything on it that would interact inappropriately with the other drugs? Have I given this drug to this patient within a certain amount of time? There's like these rules that I have to do. Now, this is where the science comes in. Let's do an order release and how much memory is allocated in order to do that. Turns out it's about 11 megs. Now, we could debate as to whether that's a good or bad thing or whether we can optimize it. Doesn't matter, though, does it? I actually know, I'm not guessing. When I do an order release, I get about 11 megs of data. That's on one order release, and I have hundreds of them happening concurrently. Now I need to know, well, what's my max? And I'm going to start throwing all these numbers together and trying to understand what size of a new space I need to have and what size of an old space that I need to have to manage this. And it turns out there's very little old space that I need, just enough for the rule space engine. And we'll see some changes in a few slides. If we put it all together, here's a nice picture that throws kind of those concepts together. I have Eden, I have objects that are moving, this is driver spaces, I have a minor GC that occurs, and then some promotions that are occurring. Let's talk metaspace. At some point, we're like, keep running into perm issues, and it's frustrating. Now, what's interesting is that we've slowly been taking stuff out of perm and putting it, and moving it around, essentially, for multiple releases of Java. This started with Java 6, as far as I remember. There was at least a release of 6 and a couple releases of 7 where we started kind of moving some stuff around to the point where we went full-on metaspace in Java 8. And what that means essentially is that if you First of all, the default is 0, which means unlimited. You are now in the native space for this, anything that remains in metaspace. And if you have a class loader leak, that means you're affecting the entire node now, as opposed to just your JRE. So you could debate as to whether this is a good thing or not. Most people see it as a good thing. It is uncommon to have a class loader leak. They do happen, but it's still uncommon. So, and what we really do have is metaspace is more meta than you can imagine. It's metaspace of metaspaces. And I don't know if I'll go into heavy detail on that, but the way it's managed is a collection of metaspaces. Essentially, a class loader manages a metaspace. And then all the class loaders make up the entire metaspace, or metaspaces. And there's a little bit of a challenge here, and that is if you previously had max perm space because the default of 32 was not big enough for you and you started growing bigger than that, you might be tempted to just put metaspace in place of perm space, and that might not be what you want. For one, perm space, bad things could happen if you ran out of perm space, where you have to bounce it. Not true in the native space, and so you may change that. But most of the flags are the same. There is a max meta space. There's one more thing, though, that's worth pointing out. I think I'm a slide away. Here's the evolution of changes that have been pulled out of perm space, as I mentioned. The new thing here that is quite different because we're working with native space is the flag for the max metaspace expansion and the max metaspace free ratio. If I'm going to be pulling things out of native space, I have a couple of concerns. One concern is if I have to go back to native space, how much at a time do I want? How much of a chunk of memory do I want to consume out of the native space? Hence the expansion. How frequently do I want to go get it, right? Those are the things that you can manage. Again, you're managing this at a native level and not inside the GRE level. Just be aware. And the default, if you don't set it, is unlimited. It's 0. All right. Is that counting down? It is. Okay, I got 20 minutes. Great. So there's a couple of slides that I'm glad are here that you could take and kind of comb through that is terrible to present to. And that's always a challenge as a presenter, is do I leave you something that you could read behind that you could take later, or something I could present to? And so I might go quickly through some of these. If something catches your eye and you say, hey, whoa, stop me, okay? Feel comfortable doing that. A couple of things. What is the frequency of GC? Really easy, the minor GC. Well, it's the object allocation rate and the size of Eden space. Those two things will predict how frequent a minor GC will occur. In other words, how much memory am I consuming and how big of the space do I have? It's really simple, right? What is the frequency of object promotion? Now this becomes important, and you can see it's entangled in the last equation. The promotion rate is going to be geared off the minor GC rate because the aging of objects will occur. So the frequency of the minor GC will impact promotions, but also the size of the survivor spaces. Because if I can't fit in the survivor space, then I have to put it somewhere. Okay, those two things will manage the frequency of object promotion. Now, let's talk, a few minutes ago, we just mentioned, like, what's the most common thing when we have memory challenges for an engineer to do? Well, just to bounce MX, right? What is a strong possibility in that scenario? I have increased the amount of memory in my old space, which means I've increased the amount of time a full GC occurs, which means I've increased the amount of time that a stop the world event will occur. And that might not be what you're looking for. It's not what you're looking for. Okay, we're clear on that? All right, some of you are looking for it. All right. All right, what we're looking for is a high morbidity rate in new space. I kind of like to say that, I don't know why, but they're really violent in America, you know that? It's weird. Still have guns, it's weird. No, objects, we really are looking for objects to die quickly in the new space. I want a new space that's large enough to tenure objects so that it will die in new space for a request-centric or microservice-based architecture. Okay? Remember, that's use case driven, right? We talked about that. It's very use case driven. tenuring, some throughputs, and things like that. I kind of played some lip service earlier to this. To actually move the pointer is 10 clock cycles in Java. A malloc takes 30, as if you cared about that. Counting your clocks. And some different promotion rate type stuff. All right, let's get to some hotspot collectors and talk about the collectors for a bit. As I mentioned before, the parallel old GC is your default. There's some things that we know about it. First of all, it's the fastest minor GC. Why? Well, because one, it's contiguous memory space. And two, I'm just moving a pointer. And even, the part that I didn't cover yet, but even when I want to clear space, when I want to reset to 0, I literally have, like this pointer right here is the start of Eden, right? And I have this moved out to the end of Eden, and I had a minor GC occur. Do you know how I reset stuff? I just go back to base 0. I just write over what was existing there before. I don't clear anything. I just write over stuff. It's way fast. I don't know if you can get faster. It's way fast. So the fact that it's contiguous, the fact that I always reset back to 0, that there's no fragmentation whatsoever makes it insanely fast. It's the fastest minor GC that you can get. It is also very predictable when it comes to a full GC. As you can see up here, it's still a pretty nice variance though. Somewhere between 1 to 5 seconds per gigabyte. I don't know if I know all the reasons for the range, but that's about the range you're going to be in. Okay? If you have a 1 gig heap space, you can expect 1 to 5 second time. Things that will impact that we haven't talked about, how many soft or weak references you're using. They have a huge impact on GC, largely because I have to keep those references around for multiple GCs in order to actually clear them. There's a number of factors that play into this. Okay? Okay, so that's the old parallel GC. There's some other details on setting values and things like that. Again, if we want to talk about it, we can. Let's talk about CMS. Now, CMS is a little special. For some reason, it has fans. And it's not clear to me why those fans exist, but the fans exist. Maybe some of you are the fans, you can explain to me, right? Not right now, but there'll be a moment, and you can explain it to me. CMS has a special place for me, and there's a window for it. Before the beginning of the window, this space right here, the old parallel GC is faster. It's got a faster minor GC. I start to have some challenges, though, where the pause times are concerning to me. And as they start to approach, it's fast enough, and then I start to approach this area where the full GCs are a little bit more than I care for, I might start dabbling or looking at CMS. Why? Because it is the concurrent collector. Now, we talk about the old parallel GC collector. Parallel and concurrent can be confusing. The old parallel collector means that there are multiple threads garbage collecting at the same time, but not concurrent to your application. The concurrent collector is that I have garbage collection happening while I have application code happening, which means I have object allocation and object reclamation happening at the same time, which sounds like a lot of homework. Right? So in order to enable that, there is some extra overhead that's expected. You can see here that the word's free list. I have to have some place that keeps track of stuff that's free. And then I can allocate things out of that free list. It enables me now you can imagine if I have objects being created and objects being reclaimed all at the same time, I'm going to have fragmentation. It's going to happen. It has to happen. At this point, it doesn't matter whether we have contiguous memory or not, because I'm going to have a fragmented list anyway. It's irrelevant at that point. Not that the Oracle VM is still going to be contiguous in nature, but it's not necessary, because I have this fragmentation that's occurring. Now, because of the free list, because it exists, minor GCs take longer. Again, they're fairly fast. They're definitely faster than full GCs. What I am doing, though, is I'm avoiding the consequence of a pause on a full GC. Now, I said there's a window. Before the beginning of the window, the old parallel GC is just faster. In all ways, it's faster. But I start to have some pause times that are concerning, and I want to, without making memory address space changes, maybe I have constraints on that, I want to see if I can do things concurrently. And I start to get some value out of the CMS. It's actually doing what I expected to do, and that is I don't have pause times as fast or as long anymore. Great. Until I get to a certain level of scale, there's another upper end of this window where you can imagine object creation and cleanup happening at the same time. At some load, I could overwhelm object creation where I have to stop the world again. When you stop the world with CMS, you're not going to be happy. It's a really bad experience. All right? And at that point, you have a situation where the CMS is just not working for you. You've hit the upper bounds. And again, this is where that art meets science. You'll have to find it. There's so many factors that play into that. What is your use case? Is it microservices? Is it Hadoop? There's a lot of things that play into that. What's your promotion rates? All these things play into that. Okay, so the tuning the CMS can give you some low latencies because you are reducing the amount of pause times. There's some huge values in there. There's one other collector that's worth talking about, and that's G1. Anybody know what G1 stands for? Yeah, and everybody seems to know that now, which is great, right? Garbage first. Here's the interesting thing about garbage collectors today. It's kind of a misnomer. They're more garbage avoiders than garbage collectors. It's a garbage avoider, right? Notice what happens. In the two collectors we've already talked about, I allocate. I then move the living or the referenceable objects over. I never touch the dead. I write over them, right? It's a garbage avoider, not a garbage collector, but old school dies hard. I don't know if that's the right phrase, but anyway, what is G1? What does it do? Garbage first. So what we're going to do with G1, imagine I have a checkerboard, and I have Eden spaces and survivor spaces and old spaces all littered all over my heap space. I intentionally fragment the memory on purpose. Now, you can imagine what would happen, right? As I fragment things, let's say I have 5 Eden spaces. And I write over Eden, and I ran out of Eden, of that region. That's the term. I run out of Eden space in that region. And I'm still writing Eden space, so it finds the next region. And I've gone through 5 of those regions, which is all that I have. What happens? Well, I do a full GC, or a minor GC. What are the things that are possible? Well, one possibility is that one of those regions, because of a high morbidity rate, has nothing referenceable in it. It has nothing but garbage. Hence, garbage first. I can now, without moving any objects around, write over that region because there's nothing living in it. Right? And you can also imagine the size of the regions will dictate how frequent it's full of garbage. So there's a number of factors that play into this, but we've intentionally created a high overhead, if you will, for the benefit of reducing full GCs by creating multiple regions for which it will be common to just write over regions without moving objects around. It's more of an object copy avoidance than almost anything else, okay? And that is the core of it. I mean, you could get much more detail, but that's the core concept, is that I am going to break up the regions of memory. And you can also now clearly see, doesn't matter if you have contiguous memory or not, because I have to manage the ranges of memory anyway. Yeah. I'm sorry, I can barely hear you. And I have like 7 minutes, so I might be quick on this. And there's going to be a break after this You can swarm me. One of my favorite pictures is I was here 5 years ago, and a bunch of people came to my hotel room, and we sat around my bed, and I have a picture, like that never happens in any other country, but people are hungry to learn here, and I love that. What's that?
How can the JVM be sure that all the garbage values go to a single region space in Eden?
So there's no manipulation, if you will, of like placement. There's no decision of placement. There is a current Eden space, and I will keep writing in that space until I run out of that space, and then I'll have to do something. Now that thing I'll have to do is either define another region, or I'll always have to find another region. But I could be out of regions for which I may need to find a free region or do garbage collection. So there is always a possibility that of 5 regions, I have some referenceable objects in all 5, and I have to move those objects around into. But you can see a little bit how tenuring is slightly different.
The usefulness of G1 is very less probable. I mean, the probability is very less to have a region with all the garbage values alone, right?
I don't know if I'm following completely, but let me move on if it's okay, because I want to finish some thoughts. But I will, please don't just go away. Let's talk about it afterward. Because I'm afraid that I'm trying to, there's still some things to cover, and I'm going to run out of time. Full GCs, we talked about that. We did the comparison of, hopefully there's a clean comparison of old parallel GC, CMS, and G1. Yeah, real quickly, some advice. First of all, if you know the size of your collections, size them. The underlying structure for all collections, hash maps, it's always an array. Always, right? So underneath the covers at the lowest level, it's always an array. If you know the size of it, size it. That seems obvious, but a lot of people don't for some reason. Never use finalizers, right? We can say that that's broken, never worked well, so don't ever do that. If you have, like you didn't write the finalizer, but somebody else did, and you have to use it, first of all, fire them, but then if you have to, notice the difference here that I have a class that's got a finalizer, and then I have something that extends something that has a finalizer, and that has a huge buffer. That huge buffer has to stick around for multiple GC cycles. Compared to this, where aggregation is much better than inheritance, which is commonly true, by the way, if we want to get into an OO conversation. But aggregation over inheritance, strongly advised, especially in this case. Some JIT optimizations that are kind of fun and interesting. Now, a couple of things. It doesn't matter how many classes are in your jar. It matters how many classes are loaded. Yeah? So you could have multiple implementations, but your Spring configuration only loads one of them. Awesome. So if you have one implementation, the JIT engine will just rip out any polymorphic behavior and put in the one implementation, we call it monomorphic. If there are 2 implementations at runtime in the class path, right, at runtime, we'll go bimorphic, and essentially it's an if-then condition, which is still relatively quick relative to a V-table or a virtual table. If you have multiple implementations, I love this word, you're megamorphic, right? In which case you're using a V-table, there are no optimizations that are possible. Code caches. There's been some updates over time in the size of the code cache with good reason. If you're running out of code cache, if you ever have an application that runs for a very, very long time, but then starts to behave really oddly, like it starts to get really slow, this is commonly a cache miss, and you can adjust that with some flags, if you will. Some quick thoughts. There is a -X and a -XX flags. The -X are standardized. The -XX are supposed to be experimental. Here's the thing, if you're configuring these things, you're in production and you rarely swap out a VM, right? Like it's at a maximum, it's every 6 months, but it's probably more like a year. So I'm just not concerned with using XX flags. I would recommend them if they make sense for you. I'm going to pass that one. Tier compilation, we don't have time for that, but system dictionary. There's a magical prime number that creates the size of the system dictionary. Also cool, could you imagine in production unlocking the experimental VM options? Like, It's like getting an award, right? It's like, you've unlocked the experimental VM options. Where you can actually have some impacts on the system dictionary. This is the dictionary, by the way, that maintains the number of classes. If you have more than 1,009 classes in your class path, this might be something to look at, okay? Or your design might be something to look at. We have the string table. Once again, we can change the size of the string table. Once again, the prime number of 1,009 is the default size of that thing. Once again, you can get some details. Here's some helpful tips on trying to get out either the number of classes that are loaded or the number of strings in the string table. Again, probably not in a production environment, but a useful tip. A quick study, and then we'll be done. We got 2 minutes left. It's working on this pharmaceutical application I was mentioning. There's a great tool out there called Visual GC. It has now been adapted or a plugin to Visual VM, which is an awesome tool, which is a part of your JDK. It has been since Java 6. For some reason, it's less frequently known. And once again, you could probably use the terminal and look at just data flowing across your screen. That's terrible. What you're really looking for is trends. I'm looking for trends. Now, this is that one application I was mentioning where I just got a lot of thrashing in here. But what one thing on this slide is most concerning? There's one thing that's just like, ugh. It shouldn't happen that frequently, and you can see it in this small range. That right there. I have old space that's down here. You might not be able to read it, so if you're far back, I get it. But I have old space down here, and when I did a full GC, look at what I did. I didn't need a bunch of stuff. I have a high morbidity rate in old space. Not what I'm looking for, right? So this is where art meets science. I did some measurements. I did some profiling. I made some adjustments. I have an 8 for my survivor ratio. What does that mean? Increase the size of my survivor space, right? I made it bigger. Okay, so a couple of things I did, and then we get something that looks like this. Same application, same basic level of load, but now I have a high morbidity rate that's happening in my Eden space, and I have a nice transition. You can even see when a minor GC occurs. There's the blip of the minor GC. I can see all these objects kind of go away except for that. I have a nice ramp up. Just so happens to be the style of this application. I would not normally, well, you do get some ramping, but probably not this smooth. Just expect some differences, especially if you're measuring production. Very good. A common question I get is, do I measure these things in production all the time? Does it affect anything? It's already affecting things. It's already there. There's one thing I wouldn't do in production, maybe more than one, but one that stands out for our topic. And that is doing a heap dump. Heap dumps are a last resort thing, or doing any kind of JMap type memory details, a last resort thing in production, okay? I get if you need to do it, you need to do it. But any of this stuff, all day long, no big deal. It's already data that's coming out of the VM. So I wouldn't have any reservations. With that, hopefully you got some value out of this, and that's all I had. We're out of time. Thanks.